So stupid. Like, do you realize how ridiculous that sounds?
Yes, I do.
So what's the point?
There is some fun.
All right. So, what is the primary difference between Android's multitasking model and iOS's multitasking model? Go ahead.
Android uses Linux. It is really efficient.
Okay. That is a difference. What makes it inefficient?
Which is built for desktop.
Okay, so it's Android's multitasking model is a desktop-based multitasking model where all the apps are actually getting CPU time in the background. Where iOS isn't even really a true multitasking model. It's the only aspect of it that really is when an app goes in the background, it registers with the operating system under certain hooks that allows you to do some operating system level stuff, like stream music and that kind of stuff, but applications don't remain running in their entirety in the background. So that's the major difference between the two. Okay.
Was it just the desktop Mac OS that uses preemptive, or?
The old desktop Mac OS used preemptive.
Okay, so that doesn't play into phone.
No, unrelated. Yeah, so you got it wrong.
Well, if you cross that part off, then I got it all right.
You just added extra stuff. All right, so here's a test-taking technique hint for you. Whenever you're confident about a majority of your answer, there's one part of your answer you're not so confident, you're almost always better off leaving that off.
Yeah.
Say what you know, don't add extra crap. What are in the TV shows, the lawyers say, don't answer questions you weren't asked or something like that. So only don't give any extra information unless you're confident in it. So I'll just give you a 0.
Okay.
Seems fair.
What's this? Yeah, it's a learning exercise. It's the only way that'll sink in is with negative reinforcement.
All stick, no carrot.
So, yeah, don't they show the video of this or in the psychology classes still about that experiment where the person's getting electrocuted on the other side? They keep asking them questions, and whenever the person answers it wrong, they get electrocuted. And have you seen this before?
Super unethical.
Yeah. Well, but the interesting thing is it's the actual experiment isn't on the person that's getting the questions asked to them. It's on the question asker. The other person's not really getting electrocuted. They're screaming and stuff as it goes in, and so the person just keeps asking questions. When the person gets it wrong, they feel pretty good giving them the light shocks, no big deal. Then the person answering the question starts making little noises when they're supposed to be getting shocked with more voltage. Totally missed the quiz.
Yep. You miss one like every day.
Gotta leave 5 minutes earlier, dude. 10 minutes earlier, actually, really. But then towards the end, these people are getting like major shocks, and you hear the people in the other room just screaming, like stop! Why can't I stop this? And then so we're watching the question asker people, and some of them are just ruthless, like when they push the button after, like what happens on the next couple after they started screaming is they stop making noise at all. Like you just think they either died or passed out or whatever. So the ruthless people, they just keep pushing the button like they think it's not going through. And then some other people say, I just can't do this. You can keep your money. They walk out. And so I don't know. I find that interesting. What would be even better is that the person was actually getting electrocuted.
That'd be awesome.
Like you lied to both people. Okay, you tell the person getting electrocuted you won't really get electrocuted.
Then it switches at the end.
Well, yeah, what you do is you make it like a 33% chance of electrocution. So like they might get through a couple and no big deal. It's like, or the first couple just hit them like, well, that was weird. It's like, oh yeah, it's a weird bypass in the system. Don't worry about it. Then they wet themselves. Best part.
It's a great game show. I'm excited for it to come down.
Mm-hmm.
You gotta start both people.
A lot of
up,
people
every
would
time
watch
you-
it. Oh, I think everyone would watch it.
That's actually what's wrong with society today. Okay? Like I guarantee, I think I've said this in other classes before, but I'll say it again because it's hilarious. So like Survivor, what are they on season 4,000 of Survivor now or something like that? The first season of Survivor, you had all these people jumping off the helicopter wearing like tuxedos and stuff like that because they went to like some banquet and they took them right from there. Well, now they all know what's coming, so they're wearing bikinis and swimsuits and tropical island gear. Why don't you just dump them in the Antarctic one time? It's like, survive! or put them in like really dangerous places.
Have you seen Alone?
Yeah,
That show? Yeah.
Survivor Atlantic. You pre-chum the water. Okay, everybody passes through a fountain of monkey blood. They drop into the ocean, center of the ocean. You're not swimming anywhere. See what happens. I mean, let God pick. Christian worldview. Survivor Antarctica would be awesome. Because you'd see a couple of those contestants pretty early on go tauntaun style on one of the other people. How many of you get that joke?
I don't think it's funny, but
What's not funny about it? This is all just hypothetical.
Yeah, but the sad thing is that
People would watch it.
yeah,
That's
why-
the whole point of this.
Yeah.
People would totally watch that.
That's why I don't want to encourage it.
You'd like to think that at some point the networks would have a moral compass and wouldn't allow that to get on TV, but I can't sit here with confidence and tell you that it wouldn't.
It would just be the lawyers coming in. We wouldn't make money off the
Yeah,
show.
yeah. If it wasn't against the law, I think they would do it.
Not even that. It's just if they would make
If it's
money
not
from it.
profitable.
Yeah, yeah. That's
It's like, we don't think the contestants are going to survive long enough to make this fully profitable for us.
We'll go sell any merchandise, so no one's going to attach to the character.
they don't get attached to the characters. I mean, the guy was in a Speedo. He dropped him in the middle of Antarctica. What did you expect?
At least 2 episodes of terrible material.
That's what they'd have to do. Is they'd have to do it like documentary style, like really stretch out the 28 minutes of footage they were able to capture. First 5 minutes was exciting, then it just really got sad. Oh, this is a pretty good start to the recording has begun, by the way. Just most of this is captured, so we're good. Oh, and for those of you who are interested, we'll be in the cafeteria around noon today for lunch. I'll have the hoverboard with me. If you want to.
Like a Segway that you can
The
just...
Segway without handles?
Yeah, the Skywalker.
Yep, it's in my office right now.
Are you gonna have it in the cafeteria?
I already had it in the cafeteria this morning.
I've seen like 3 gifs of ladies just beefing.
I have a video of Dr. Jastrom, chair of theology, writing it.
What does it cost?
Huh?
How much does it cost?
Like 800.
Why doesn't everybody have these?
Exactly. That's actually the more expensive one that's made out of steel. They have aluminum ones you can get for like $350. But that wouldn't quite hold my robustness.
All the others just run people over in the walls.
You had to get the
I've
titanium.
Well, so
Yeah.
cafeteria at noon. So it's only for 5 minutes on it. It's $10. Each additional minute's $3.99. So good deal.
I pay with Bitcoin.
What if I just want my picture on it?
How much is this falling in?
You could write it for free. Okay. I already got stopped by campus safety this weekend too. They saw me whipping by the cameras at 10 miles an hour. They sent up 2 officers to check what was going on. All right, so let's pick up where we left off last time. So last thing we kind of talked about was we were talking about fragmentation. We talked about the quality of the App Store, kind of different approaches that Apple and Google take. Google takes the approach of we'll let you put anything on the App Store, and when somebody complains, we'll take it off. Apple takes the approach of only if we approve it does it go on the App Store, and whether or not we approve it is a completely random thing. Okay, it can't have crashes, no pornography, stuff like that. And even if we just don't like it. Like in Apple's documentation somewhere, there's I think a quote that says something along the lines of we don't need any more fart soundboards or farting apps or something like that. Because those were the really popular ones the first year of the App Store, the ones that made the different fart sounds. And also the lightsaber one. Where the lightsaber?
Yeah.
Huh?
The gun one.
Yeah.
Were the really simple ones, like the beer pouring one?
Yeah. So those were, neat from a, hey, this is what the technology can do perspective. But we're not impressed by that anymore, right? We've become desensitized. So now when we download that by, early day standards was like an amazing app. We download it's like, well, this is worth 30 seconds of my time. I don't even know why I used my data plan to download this. This is garbage. All right, so really, in the end, punchline today is Android has evolved a lot towards a mobile-centric operating system, away from the desktop-centric operating system. iOS has continued to evolve and really has started to incorporate some of the Android innovations into it. So in the end, what we really have is we have two mobile platforms today that we could call relative equals. The greatest advantage you probably get on the iPhone side of things is the fact that it's the hardware and the software are made by the same people. So that's going to give them an edge from a usability perspective. But that edge is very, very thin at this point when you consider how good Android is and how there's like 4 or 5 Android devices that have kind of risen to the top as being like your premier ones. Like you have your premium Android devices, so those would be probably the Galaxy devices, maybe one of the HTCs. There's probably one more. What would
Nexus.
you? Oh, the Nexus. Yeah, the Nexus. I don't. Are they premium just because they run vanilla Android?
I think Nexus 6 is up there. At the top.
Okay. Well, so you get what I'm saying. There's 2 or 3 or 4 kind of high-end Android devices, and they're all pretty similar in terms of screen size, that kind of stuff, right? We've kind of settled in on the smartphone screen size is like 4.7 inches-ish, right in that ballpark. So whether it's 4.6 or 4.8, the apps are going to look pretty similar on those. And all the devices today pretty much have a similar resolution and aspect ratio to them. They have the ones that are the 4K screens and stuff like that, but really stuff's just going to start looking smaller on the screen. The aspect ratio is sort of kind of stabilized on the Android side, at least within maybe 10%. So you don't really have this giant gap in apps. In the early days of Android, you had some devices had the very, very small screens, like flip phones that had Android on them. And then, you had actually you didn't even have the giant ones at the beginning, but, there was a lot more variety in smartphone screen sizes early on. So as the hardware has evolved and users have kind of picked what they think their favorite, really smartphone size is now the 4.7 and the phablet size is like the 5.5. And after that, you start getting into tablets where it's a little bit different ball game. So really, we're stuck with kind of 2 sizes for our smartphones.
This site that I use for responsive widths.
Yeah.
And for the description for the Android device, the crappy Android device.
So they say they say crappy Android device?
Yeah.
Oh, nice. Okay. But as our hardware has evolved, the developers have had to make things work for less devices. They make it work for the 95% of the people that are using mainstream Android devices that it's going to look fine on. And then also, so it's almost maybe become harder on the iOS side as a developer. So initially, I would have said it was much easier for an iOS developer to write software because they were only targeting one screen size. Well, as iOS has gotten more fragmented, you also, I'm not saying it's uncommon, but it's probably more common for people to be running older iPhones that are running smaller screen sizes than it is for people to be running Android phones that are running smaller screen sizes because Androids have had the larger screen sizes for longer. So any of you in here still running a 3.5-inch iPhone screen? So 4 or 4S?
Temporarily.
Okay, temporarily, but so you're still running it and it works, right? So the latest OS is maybe a little bit sluggish on it, but not horrible. Okay, and that's not like that's not an unfound situation. So there's plenty of people still running 3.5-inch screens. There's plenty of people still running the 4-inch screens from the 5s. And then we have the new group of people from a year ago that are running the 6s, the 4.7-inch screen. So as a developer of an iPhone app, at the very least, you probably have to target the 4 and the 4.7-inch screens. Maybe we omit the smaller group of the 3.5-inch screen users, but you're still targeting 2 separate screen sizes. Where really Android, there aren't many devices somebody would buy today that's going to be a 4-inch screen on Android. They're all going to be the larger screens. So it's almost become come full circle where iOS is harder to develop on now because you really do need to make your app fit for more screen sizes. Or Android, you have the ability to do so, but you don't really have to. So, interesting punchline. Okay, so we started talking about the reduced instruction set type CPUs, and this is another full circle type thing. So we're back to kind of the Apple versus Apple versus Microsoft war, but really it's the Apple. This is talking about hardware. So Apple hardware historically ran on PowerPC processors. Okay, so PowerPC was a processor made by IBM that they were having some developmental issues with it. Now, what does it mean for a processor to be reduced instruction set? I think I at least verbally mentioned this last time.
Not last time, maybe 2 times.
2 times ago? Whatever. Yep.
There are less like magic tricks for the processor.
Okay. So at the end of the day, we have to solve our problems with less tools in our toolbox. But each one of those tools might do a little bit more than the equivalent-ish tools on an Intel processor. All right, so in a reduced instruction set situation, we have less tools that are available to us, but we still are solving all of our problems in terms of the tools that are available to us. One of the issues with reduced instruction set, and it's almost like it becomes a chicken or the egg problem. What do you think was the motivation for reduced instruction set CPUs in the early days of CPU architecture? Go ahead.
Specialized devices.
Okay.
Get like specialized devices or
Not what I was thinking, but that's true. That's true. I mean, if you are creating a microprocessor for a very, not a general purpose computer, but a computer that does something very, very, very specific, then you're obviously not going to have 4,000 tools in there. You're going to have the 7 tools, which are the things that it needs to do. So that's a true statement. But in terms of general purpose computers, what do you think was the motivation for reduced instruction set? So the hint is that in the early days of the Mac OSs, they used reduced instruction set processors. But now it's relatively uncommon for reduced instruction set. Well, let's say it's completely uncommon for reduced instruction processors to be on desktop computers. Why do you think that is?
Memory speed, memory problems.
Okay, what do you mean by memory problems? Yeah, that's completely wrong what you said.
You have reduced instruction set, so it takes up less memory than
Okay, you're going on the right path. So certainly, I mean, there's some truth to that, because certainly we can only put so much memory on the chip. But when we think about building a processor, are the instructions something that we write in software then store in memory? How are the instructions represented? Yeah, hardware, right? You know, logic gates and transistors and those types of things. So really computer programs written in hardware. So back in the early days of processors, would you suspect that we can fit more or less of those hardware-based computer programs on the chip than we can today? Much less back then than we can today, right? By a lot. Okay, I think I mentioned it in passing, either last class or 2 classes ago, or 20 classes ago, or last semester at some point. But you've probably heard me say it. When you on laptop computers, sometimes when you look at the processor, it'll give like a measurement like 0.13 microns or something like that. Okay, what does that mean?
distance between each switch.
Yeah, because we print our circuit boards now. You know, they make a prototype where they have some dude with a soldering iron who builds out all the gates to make it work, and they say, okay, well, we've tested that this works. Now we need to integrate this into something that's going to fit, on the head of like a pencil. So human beings aren't getting in there with the soldering iron, so we need to get something. So we print our actual circuit boards, and that 0.13 microns really deals with how close we can print those wires, let's say, next to each other without them conflicting. At the microscopic level. At what point is one metal atom touching another metal atom and causing interference and that kind of stuff? So as our technology's gotten better, we've been able to squish more of that stuff onto a single CPU. Now, so in the early days, the battle, I think somebody mentioned it last time, has always been with hardware, has always been heat. Okay? Was that you that mentioned it last time? You mentioned it last time. Okay. Yeah, you're not very memorable, actually. So the battle's always been heat. And you didn't even wait. You waved at me, but you didn't know you waved at me this weekend when I came through the. That's yeah. You say you don't look at people. I'm not in my regular car.
Oh.
My regular car is still in the shop. Like my guy hit me on the interstate 2 months ago.
When I see like the Ford, like your car, though, I always like look to see if it's you. So.
Well, now you're just backpedaling.
No.
Oh, I think I got an email from that guy this morning. Let's see what he said. Let's see.
Doors are back ordered. It'll be another month and a half.
I think it was something like that. Oh, here it is. Let's see. It's painted now just to reassemble. It will be done this week.
How long ago was that?
Well, that was this morning, he said. But last week, he said it'll be done by the end of that last week. The week before that, he said it'll be done by the end of that week. The week before that, he said it'll be done the end of that week.
So it'll probably be done this week then.
And the week before that, he said, oh, I'll only need it for 3 or 4 days.
So it'll be done by December.
Hopefully.
At least they got me a loaner that had a trailer hitch so I could keep fishing.
So, what did he say it was going to this morning? It's painted and it's ready.
Everything's painted. They just need to reassemble.
Hold on.
Here, I should reply back real quick and make sure the Xylon coat.
That'll be after 2 weeks.
So, in any case, back in the early days when they were making these processors, we had, heat's the enemy. We can only fit so much stuff on these processors to begin with. So there might have been some motivation to have less magic tricks that they have to build onto the processor to have it be a less crowded city, if you will. If you think about the processor as a bunch of buildings that make up a city, less crowded. We can't make our processors this big. Well, I suppose you could, but your machines wouldn't look that cool. So processors kind of have a standard size, and they really haven't changed size. Those of you who, how many of you in here have built computers for like kind of a while, several years? Okay, so something you've probably noticed is that the actual physical size of that processor has not changed. What's changed?
Size of the motherboard?
Okay, heat sinks have gotten bigger, okay, because the processors are giving off more heat. What else has changed as far as the CPU itself? What's changed on the CPU itself?
Shinier.
Okay, which translates into what? When you flip that CPU over, what do you see? A lot more pins. A lot more pins. If you look at a CPU from late 90s, you could basically fit your finger between the pins. Okay, now, the pins are like at the kind of like the bed of nails type of like nothing fits between the pins, right? I mean, they're basically touching each other just about, right?
Don't like all the Intel processors now don't have the pins anymore, so
Yeah, so it's now it's based on a magnetic connection where it's still the same thing, but it's less of a physical presence for the pins. But the point is that when you flip it over, there are more stuff, more things for the motherboard to have to interact with, right? And in the early days, you used to bend pins fairly often. That's when they came out with the ZIF sockets, the zero insertion force sockets, where you open it up and you just drop it in. Before that, you bend a pin, and then you're trying to straighten that one out, and you bend the one next to it. It's like, oh my gosh, and all that stuff. So, in any case, the motivation in the early days was we want to reduce heat. How do we reduce heat? We reduce the number of things, the number of magic tricks we have to build. So in order to do that, we need to come up with this set of magic tricks that still let us solve a generalistic collection of problems, but with less Legos to solve them with, less magic tricks to solve them with. That makes sense? Okay. Well, so what ended up happening is in the early days, IBM had issues, and IBM wasn't the only one making these. There was several other companies that made their own silicon that had that were reduced instruction set type processors because on paper they were easier to make. Okay, but just because you have less magic tricks doesn't mean you're going to have less heat. If you're going to try to solve the equivalent problems with less magic tricks, what do you think that means for the average size of a magic trick? Average size of a magic trick is probably going to be a little bit bigger, right? If you want to house all the people in, so we've seen this in Japan. Okay, if you want to house the huge population that's in Japan in the same footprint, what do you have to do? Build up. Right, so they got skyscrapers of apartments. You know, I live on the 203rd floor of the whatever building. So we're having to put bigger buildings on there, but just less of them because we don't have the footage, the square footage to put them. So these guys actually suffered from heat problems because our evolution of the anti-heat stuff wasn't where it is today. So reduced instruction sets were made to fight the problem of heat. Yet they actually suffered from the problem of heat because representing less tricks with more complex tricks ended up working against them. That's what happened in the end.
So they're made to solve the problem of heat, but they suffered from it?
Yeah, I think it's fair.
So with cooling technology where it is now, could these come back, or is it are they pretty?
They have. They have come back, and we've probably all heard of them. ARM processors. Most of our mobile devices today have ARM processors. All of iPhone's processors are ARM processors. The octa-cores that are in some of the Android devices, those are ARM processors. So those are all reduced instruction set processors. So now that goes a little bit what he was saying about it's solving a little bit more specialized problem. Now, I mean, we are more and more, we see less differentiation between something like this and something like this, right? We in our mind, it's less separated. This isn't a phone and this is a computer. They're both kind of computers now, right? But we can probably assume that there are less magic tricks this guy needs to know how to do because of the types of problems we've kind of, is it evolved or devolved to what we solve on our smartphones? But whatever. But also, today our technology is substantially more appropriate for approaching the reduced instruction set problem. Kind of makes sense. So maybe it was a little bit ahead of its time, kind of like AMD and their 64-bit processors way before operating systems were 64-bit. Okay, so that's reduced instruction set. Already talked about that. Yeah, you talked about the operating system acting as the layer. So now we're kind of moving more into the individual parts of our operating system. So let's jump ahead here. All right, so our operating systems, we want to think of our computers as collections of resources. Okay, so and now we want to start focusing in a little bit on what the operating system's actually doing. So if we think of our computers as collection of resources, as a collection of resources, we want to think of the job of our operating system in general from a hardware perspective, not from an interface with a user perspective. So we're looking at the underside, what's under the hood now, is how do we efficiently manage those resources? Allocate them to who needs them, deallocate them when they're not being used, and make sure everybody can use them when they're needed, but making sure two people aren't using the same resource at the same time unless it's a resource that can be used by two people at the same time. Make sense? So these are all kind of the micro jobs that an operating system has to do, and everything can be dumbed down to this idea of it's a resource, how do we control it? And we solve these same problems in real life. You run into a McDonald's, only one person can order at a cash register at a time. So human version of the solution is we form a line. An ATM machine, only one person can use the ATM machine at a time. So we form a line. The soda machines at a McDonald's usually have 5, 6, 7, 10 sodas on them, right? Well, as long as 2 people aren't going for the same soda, they can use the machine. More than one person can use the machine at once. So different types of solutions for a similar problem, right? Things get a little creepier when we start talking about managing the urinal resource and stuff like that.
Technically, 2 people can use it at the same time.
followed by somebody serving papers. Although I think that in some foreign cultures, it's not uncommon for there to be, like in restrooms, there just be basically a trough where you're just sitting right next to people.
Oh, that happens here. Have you ever been to a NASCAR event? Just have troughs.
Well, no, that's for number one.
Have you been on?
I'm talking about the
Have you been
all Roman style.
You're not supposed to use that?
Have you been on a military post? We do that all the time.
I thought that's why we had the elongated bowls. You just hop on somebody's lap.
Oh, I was on a
That kind of grossed me out a little bit.
I was on a range in Michigan for the Army, like on a gun range. Yeah, we walk into the bathroom and there's just 6 toilets.
Yeah.
Just all in the same.
Yep.
Just hand around the toilet paper to your buddies.
Yeah, I mean, so the punchline is that in general, I mean, we got off on the funny tangent, but in general, the human solution to some of these resource allocation problems is going to be similar to the types of things we're solving in computers. What's the difference between sharing the CPU between a bunch of programs and sharing the cash register at McDonald's between a bunch of hungry people at lunch? I mean, it's a very similar problem, right? But then our operating systems get more complex as our CPUs start getting a little smarter. Now we have CPUs that have dual cores or quad cores. So now it's like in real life, it's that, 4-headed cashier at McDonald's that can technically take 4 orders. Just painted an image there. That could, we call it the mini Hydra. The McMini Hydra. The McHydra. It's good. Hey. So anyways, where you have a cash register that could legitimately take 4 orders at once. We can understand that, even though that we're not there yet in real life, we can understand that would certainly increase the complexity of how we would solve that problem. One line is no longer going to cut it, right? And we've, how many of you have ever been to a Cop's custard burger place around here? How many of you have been upset by the organization of how ordering occurs at Cop's? They've taken what seems to be a simple problem and they've changed it to try to make things more fair. So for instance, at Cop's, there's 2 lines if you're doing just ice cream. Okay? Cones and dishes, but not sundaes or shakes. Sundaes or shakes need to be ordered through the grill line. You can't order a burger through the ice cream line. You can order a burger through the grill line, but you can order a dish of ice cream through the grill line as long as you're also ordering grill food, burgers or something. Why can't they just make every register do the same crap? Is it really that big of a deal? So, Although, in their defense, I've been in there and the lines can get pretty long. So, it actually is beneficial, I would say, when you're in there for ice cream, to be able to just get in the ice cream line, which moves pretty quick.
That's probably why they do it entirely, is because they have enough people coming in for just ice cream.
Yeah.
That having all 3 lines for everybody.
So, it's really situational of whether I'm upset or not. Because this is what happened one time. One time I was in the ice cream line, got up to the front of the ice cream line, and I wanted to order a turtle sundae. They told me I can't order it there, so I went over the other line. In the process of being in the other line, I noticed that the flavor of the day, which you can order in the ice cream only line, was something that I actually liked. So by the time I got to the front of the grill line, I had changed my mind and wanted the dish of the flavor of the day, which can only be ordered in the ice cream line.
Have fun.
So it was my own fault, but I still got mad at them.
Yeah, they don't really have like instructions that tell you that. You just kind of have to know.
Yeah, you got to be a regular. So good. All right. So in any case, I want us to start mentally thinking about operating systems from the under the hood point of view. We've all got plenty of experience in interacting with an operating system as a user. Right? So in here, what we really want to focus on is the operating system between the software of the operating system and the hardware of the computer and what's happening under the hood. And most of that is going to be resource allocation, resource management type problems. Okay? So think about McDonald's or KFC or whatever your favorite place to get diarrhea is.
Taco Bell.
This made me think about you yesterday.
Oh, that was so close.
That's where context is important. I'm not going to give it that way. When I make a diarrhea comment and then I say something about that makes me think about you yesterday and leave it at that.
I wasn't sure if I was gonna make it.
All right.
Did you?
Barely. Oh, maybe a little.
All right. So anyways, let's keep trucking here because I'm gonna give you another assignment. So this is kind of that slide that talks about what I mentioned day one. What we think of as operating systems is actually a distribution. The actual operating system is a kernel, but realistically, we have used them ubiquitously now, right? When somebody says Windows 95 or Windows 98 or Windows 2000, it's okay for us to say that's an operating system. As computer scientists, we should understand that it's the kernel itself. That's the piece of software that lives underneath all of the fluff that actually does the resource allocation and enables that pretty user interface to do all the stuff integrated, interfacing with humans to pull off the full experience of the distribution. Okay, so let's see. All right, so bootstrap program. So now we're under the hood type thing. So we kind of talk about the layers of things that happen inside of our computer. So let me draw a little a picture here. I like drawing the pictures. I don't get a blank slide here. I got to do this kind of blank slide. Always got to have the dinosaur on it.
Look at the dino, it's so adorable.
All right, so when we think about our computer, there's going to be a couple of layers. All right, so let's actually start at the top and move down. So up here, we have the user. Okay, up here we have the user. And the user is speaking through the windowing program, windowing software. Okay? So that's going to be what we think of as the user interface, the start button and the graphical stuff. The windowing system is going to be talking to we're going to say kernel generically. But now we're going to split the kernel out into a whole bunch of resource management tools. But for the sake of argument right here, we're going to just say resource managers. All right, and we'll just leave it at that. We're going to be talking about those individuals. But for this, so they're going to be, the kernel is made up of a bunch of resource managers. So this is all kind of one thingy, okay? Now, this kernel, though, lives in memory, okay? So let's give ourselves... Really, all of this lives in RAM, but let's just pretend like it's just the kernel stuff that lives in RAM. Okay, when I say RAM, that's not hard drive, that's our random access memory, like the 8 gigs, the 4 gigs, the 16 gigs of RAM that's in your computer. So RAM is fast, right? The idea is that the closer we get to our CPU, and the smaller in general, the smaller the amount of maximum memory you have, the faster and more expensive that memory tends to get. All right, so System RAM, 16 gigabytes of RAM, is fairly inexpensive today. The next layer down would be like L3 cache. L3 cache, not going to get into it too much right now, but it's RAM that's a lot smaller in size, a lot more expensive per byte, let's say, and is much, much closer to the CPU, therefore communicating with it is much, much faster. Okay? L2 cache is even closer and even faster and even more expensive. L1 cache is even closer and even faster and even more expensive and smaller in capacity, so on and so forth. So as memory gets closer to the CPU and smaller, it gets more expensive and faster. Go ahead.
Is L3 cache or cache just like a synonym for ESRAM?
L3 cache would, you said, is it a synonym for ESRAM? I don't know if I'm familiar with ESRAM, but I would say the answer is no. Okay, I mean, there's ECC RAM, which is like error checking, error control and checking RAM that a lot of servers use. But that wouldn't be it. L3 is a really tiny amount of memory that actually is shared between multiple CPU machines. So it's, or multi-core machines. So the cores can communicate with each other through L3 cache, where L1 and L2 is specific to a single core. So without knowing what this other kind of RAM is, I haven't heard of it. So either it's something I'm not aware of, or you have the wrong name.
ESRAM.
One of the two.
ESRAM is kind of primarily used in terms of with a graphics processor.
Okay. So
I
is
had
it
a lot of consoles.
is it working cache for? Is it a cache thing for GPUs? If that's the case, it may be similar to what you're talking about. If it's memory that sits next to individual GPUs in a graphics card.
Yeah, it works directly with the GPU.
Okay, so
Yeah.
GPUs in a graphics card, like I think we mentioned in the earlier class, there's like thousands of them. There may be 1,024 cores in a GPU. So it's possible that there are some fast memory locations to share between them. If that's called ESRAM, then that would be very similar to L3, similar type of a job. All right, but for our point here, it's not important to know the difference between those guys, so I won't quiz you on what's the difference between L2 and L3 cache, at least not yet. That's not the point of this. The point of this is, where do our programs have to live in order for us to experience them as a user? All right, so ultimately, our programs live on our hard drive for long-term storage, but when we're starting our computer, when it's booting up, it somehow has to get from the hard drive and load it into RAM for us to work with at high speed. Otherwise, our computers will feel really, really, really sluggish. Okay? So, faster your RAM and the faster the processor can eat instructions from the RAM, the faster your machine will feel. Okay? And that's why adding RAM to your machine often can increase the speed of your machine if the problem you're running into is low RAM. Because something we're going to talk about in here is memory management, allocating and dealing with the resource that is memory. And part of that is when you have a bunch of big programs running in your computer at once, and you have, let's just, so it makes sense to us, let's say we only have 4 gigabytes of RAM in our computer. Chances are we can't fit every part of all of those applications that are currently running in RAM at the same time. So there's going to be time periods where we are trying to use an aspect of a program that's not currently in RAM, and something needs to happen for us to jump to the hard drive and bring something into RAM, and probably swap something else out of RAM. And one of the things we're going to talk about in here is, what do we swap out? Who's likely not going to be picked for the team next? That's the person we don't need in RAM. We need the other person who's currently on the bench brought on to the playing field. Okay? So these are all things that the operating system's doing under the hood. But ultimately, our kernel, the operating system itself, somehow gets into RAM on our computer. Okay? Now, the way it's going to ultimately get to RAM on our computer is from something called the Bootstrap program. All right, so the Bootstrap program actually lives, let me steal this. inside of something called the BIOS. Okay, so the BIOS is a hard-coded. I realize we're out of time. Let me just finish this comment. Is kind of a hard-coded chip that lives on the motherboard itself. And nowadays they're called firmware because you can actually flash them and overwrite the software to them. But its job is when you first power on to take whatever your operating system is, and that's an important part to how operating systems work, and load it into RAM. Okay, so that's what that bootstrap program is. It's a piece of software that lives on a chip that lives on the motherboard. Okay, and it existed before your operating systems. All right, I will see everybody on Wednesday. I'm going to give you another assignment out of the book, but I'm only going to give you a couple of questions to do for Wednesday. Yeah, but it won't be like what I've been giving you, like 7 or 8 questions each time. I think I'm probably going to give you like 2 or 3. I'm going to pick and choose ones related to what we're just talking about. So it'll be a smaller assignment just to kind of keep you rolling. Okay? So I'll put that up here in about 5 minutes. I'm going to my office.
Questions.
No. Well, they might be. They might be. I have to look at the question options, but I'm going to selectively pick a couple of questions that are appropriate on what we're about to talk about. Okay? Not just kind of cover all busy work.
There was you didn't assign between ID homework, right?
I did not. I thought about what would make sense, and then I decided anything I give you would just be busy work. So you'll have some today, but we didn't cover enough to get where I want to go. So because we got stuck in that string stuff.
Oh, it was the difference in multitasking between Android and iOS.
Would you have known the answer?
Difference between
What's the